Okay, thank you very much. So I changed the title of my talk. So if you heard the last title and you're noticing that there's a mismatch, it's not, you're not going crazy. After spending most of the morning listening to talks on digital electronics and the importance of memory and computation, I decided that even if we made memory and computation free, we'd still have to deal with communication. And that would still dominate the power budget of our systems. And therefore, I wanted to focus most of what I, as an analog designer, with a double hard problem, as you mentioned before, I wanted to focus a bit on wireless circuits and communication and that side of things. And plus, I am focused for the last 10 years of my career on wireless design. So let's start out with this canonical, rather dull slide about radios, for those of you who are not familiar with radios. So 120 years ago, this was a radio. Okay, it was a big box that was primarily used for receiving, okay, just for listening to someone else's conversations or listening to music or something like that. It was a standalone system. It became smaller with the invention of the transistor, so now we had a smaller standalone box that was able to listen to music or talk. Then in my lifetime, actually probably in my 20s, then we got to the point of being able to do both transmit and receive on the same block. And so we could use this as a wireless medium for transmitting and receiving very basic, very simple information. Then that became a single chip. Okay, so that large system got fused into a single chip. And now we're at a point where we have, not only is that a single chip, it's a piece of a chip. It's an interface on a chip. Okay, so we've gone in the last 120 years from the point of having radio as system itself to radio as interface. Okay? What does that mean? That means that this is kind of like I/O. Now, a radio is not, radio designers can't really think about the radio as a standalone system, something that we want to design as and optimize as the single chip. We really have to think about it as a way to pipe information between other systems. And this, in my opinion, is an analogy to the way I/O was 15 or 20 years ago. In I/O systems, high-speed I/O used to be the domain of analog designers, where we would use it. High-speed I/O is a primary data pipe for data in and out of the chip, had lots of different standards, and really most users who are designing the internal stuff in that chip don't really want to care about the I/O. Okay, they kind of ignored it. I think that wireless is really the new I/O. Okay, so again, it's the primary data pipe in and out of the chip. There's lots of different standards, most of which probably a lot of you don't even recognize. Okay, but all of these are different wireless standards. And users who want to build, for instance, IoT systems don't really want to care about what those standards are or design to them. Okay? So what does that mean? If everything's going to be connected in the wireless world, what does that mean for us? In terms of new devices, what can we do? On the receive side, we have an LNA, which is a low noise amplifier. We have an oscillator. There are advanced devices that can help with the design of LNAs and oscillators, but mostly very good switches aren't so great for this. Okay, so mostly we can benefit some from advanced CMOS processes because we get higher FTs, and we can certainly benefit from MEMS devices in terms of high quality oscillators, but most of the devices we've been talking about since we've been here don't help that much with these things. What about the transmit? So in terms of the power amplifier and the oscillator, these are the big power hogs on the transmit side. New types of CMOS like LDMOS help, okay, because they enable us to do CMOS type power amplifiers, and GaN devices help. But again, very good switches aren't so great for getting watts of power out of your radio. But that's not all there is to a radio. There's also timing. Okay? If we want to actually maintain very low power operation, we need to care about the timing of our communications, and I'll talk more about that. We also have baseband processing. So these are places where I think really new devices and the stuff that we're talking about here can contribute. And the types of devices that I'm going to talk a little bit, I'm not a device person, but I'm going to talk a little bit about the types of devices that I think can contribute, which include memristors. I think tunnel FETs and steep subthreshold curve type devices can help a lot, and also potentially spintronic devices and spintronic oscillators. So I'll talk a bit about that. So to start with, how can new devices help wireless? So if we look at IoT systems and we look at the power supplies that we have available, we see that let's assume that we want to consume 100 microwatts. Okay, that's our power budget. That's an aggressive power budget, but let's assume our entire system consumes 100 microwatts. That means that we can be powered by a lithium-ion battery for 1 year, if that's our average power consumption. If we look at the power density for solar and vibrational sensors, we see that for solar indoors, we can only get about 6 microwatts per centimeter squared. Okay, so that's going to limit our power budget pretty severely. And if we go to solar outdoors, it's better, but you need to do some kind of harvesting and storage if you're going to do that. And then vibrational tends to be better than that. So this is the range of power that we need to work in. What does this mean for our wireless systems? It means that low power is going to be key. Okay, and power trades with data rate, right? We all know that power trades with data rate in radios, but kind of. Okay, that works to some extent. So if you look at kind of traditional trends of data rate versus power for a radio, you see this type of a curve. And it does look like power trades with data rate until you get down to that bottom left-hand corner, at which point there's nothing there. Okay? And the reason why, and this was, I think we made this curve back in like 2009 or something like that, but there was really nothing there. And the question is, why is there nothing there? Is there nothing there because people just don't know how to design good radios? And that is not the answer. Okay? The reason why there's nothing there is because it is fundamentally, a narrowband radio has a ton of overhead associated with it. Okay? You need to power oscillators, you need to power mixers, you need to power all this stuff, and it prevents you from getting down into that very low power regime. Okay? So what you need to do if you want to get down into that low power regime is you need to turn your radio off. Okay, so if you want to operate at low data rate, you need to say, okay, I have this overhead associated with my radio, so I get very good nanojoules per bit if I send a lot of bits very fast. But then but the rest of the time I have to be off, and I have to be very well off. Okay, so no leakage. Okay, and so what does that mean? That means that I have to figure out a way to clock my communication somehow, because I want my transmit and receive to actually be able to talk to each other. Okay, so there's really 2 ways of doing this. One is asynchronous. Okay, the first way of doing it is asynchronous, and you guys probably have heard of this. There's been a lot of this talk about wake-up radios. So what a wake-up radio is, it's basically an asynchronous radio. It's an event-based radio that has kind of 2 radios associated with it. One is the high-power radio that's actually going to do the communication, and the other is this latent, low-power radio that sits next to it, oftentimes just a receiver, and it waits. And it waits for and it's actually a horrible radio that consumes very little power and has probably very poor sensitivity. And it sits and it waits for something to bang it, okay? And when that thing bangs it, it wakes up, and then, oh, I just said that. And then it commences communication, okay? So then it does kind of what you're used to in an asynchronous system, which is some type of handshaking in order to start some kind of communication. So this is one way of doing things, and I'll talk about how new devices can help here. And the other thing is synchronous type communication. So that means, let's say you don't want to have to do this handshaking every time you want to transmit data. Let's say you have relatively high number of events. Then this asynchronous version doesn't work very well, okay, if you have a high number of events. In that case, you probably want the transmit and receive to share a common time scale. The problem is this requires clock distribution. Okay, and that's a really hard problem for a wireless system. It's easy if there's sort of one node that's governing everything, but once you have a distributed system that you can't necessarily control, it becomes quite a bit more difficult. Did you have a question? Yeah.
Yes. What about completely asynchronous? Wake up, throw the data out, go to sleep.
You still need handshaking.
Well, statistically, at some point, you get the data.
Well, okay, if you want really, really terrible data rates and really high error rates, there's probably other things you can do. But for most conventional systems, you actually want to have the transmitter on when you're receiving. But there are other versions of this asynchronous that are not wake up, where you have a regular wake up, okay, where you have something that's sort of, oh, okay, I'm going to wake up according to my local clock, and you're just sort of hoping that your local clock overlaps with whatever it's sending to you. And it might take a lot of cycles for that to happen, but that's an alternative version of this, okay, and that does exist. Okay. So this, I think the synchronous, one potential advantage, I'm not actually sure how huge an advantage it is that you don't have two radios. Okay, you have one radio. Okay. So let's talk about this asynchronous version first. Okay. So this is actually a device problem in my opinion. Okay, because really these asynchronous wake-up radios are very, very simple things. They're simple animals. They're essentially these very, very low sensitivity radios that exploit a nonlinearity in a device, okay, to do basically what we would call either envelope detection or self-mixing, okay? So they're exploiting a nonlinearity to take, for those of you who are not wireless people, because that probably sounded like jargon, you're exploiting the nonlinearity in the device to take a signal, mix it with itself. What will happen? You'll get something at twice the frequency and you'll get something at DC. You detect the energy at DC. Okay, that's really all you do. And the thing is that this requires very high transmit power because they tend to be low sensitivity at low power, and it limits the range of communication that's possible, okay, unless you have a ton of power you can throw at this thing. So let's look at what that means. Okay, so let's consider dumb input, okay, just a cosine or a sine wave, okay, incident on a subthreshold FET. Okay, if we consider that, we can compute, okay, let's say that for a given bit error rate, we need a certain SNR after our detection, okay, to get that SNR. We can basically compute what that is. We can say I out over the noise, okay, and that's the noise added by this device, okay, and I'm going to assume that n is approximately equal to 1, probably not quite 1, but I'm just going to assume that for simplicity. And we also see that GM is related to I over VT. Okay, now what I can do is I can basically take that input and I can Taylor expand the input as it reaches the output. So this is the function of this device, Taylor expanded. Okay, it's a nonlinear device. It's in subthreshold. I'm just doing the expansion of that. I can then also filter. I'm basically only using the nonlinearity, remember, so I'm going to filter out the high frequency component. And this is what I'm going to get. I'm going to get that SNR. So what is this telling me? This is telling me that I have my SNR is directly related to VN. Okay, because basically most of this stuff is kind of constants as far as I'm concerned. I can't make delta F too small because I run into 1 over F noise. W over L is going to become leakage. Okay, so I'm kind of limited by a lot of this stuff. So this is really all I have control over. So that's kind of why my VN my sensitivity kind of stinks for this thing. Okay, because I'm fundamentally limited by VN. So now what happens if I change the device? Okay, so I'm claiming that I'm limited by the subthreshold slope. So let's say I can change the subthreshold slope. I can send it to 0 and make it something closer to an ideal switch. If I can do that, I can rewrite my SNR in terms of the subthreshold slope. And I see now that my SNR is a function of the VN, again, but also a function of 1 over S. Okay? So if I can send that 1 over S, if I can send that S to 0, I can actually get very, very good SNR with very, very small VN. Okay? It's kind of logical, but this is the mathematics behind that. So a tunnel FET is not necessarily just good as a switching device in the digital domain, but it actually helps wireless also, potentially, because it means we can use it as a switching device for a radio to wake it up. Okay. The other thing, of course, that's important is that we do, which as was mentioned in one of the talks this morning, is that this characteristic often trades off with the on-off ratio, which isn't so great for this, because we also want a high on-off ratio, because we don't want this thing to leak, because then all the time when it's off, we're consuming power. So, so you need to solve both those problems, which is kind of elusive. Okay. So let's talk about the next piece, synchronous jitter and scaling. Okay, so I so far have talked about asynchronous radios. Now let's talk about synchronously clocking radios. Okay, so if we look at synchronously clocked radios, we see that the power, again, if I assume that I have two things sharing a common time base, okay, that the power of my receiver, because I'm going to turn off my receiver if I can clock them together, the power of my receiver is going to be dependent on how often I'm active plus leakage. Okay? And how often I'm active is going to be very dependent on my noise. So if I have timing noise, I have to be active longer. And it's very logical. Okay, so this is a picture of that. Okay, and it's kind of bad resolution because I took it out of one of our papers, but it's basically showing that there's some noise associated with your timing, and you have to kind of over-provision for that. So that means you have to be on. Your receiver has to be on for much longer than you would ideally want it to be on. Okay. So low relative jitter is important. And it turns out that it is actually not that easy to make low power oscillators to support this. Okay, because low power oscillators tend to trade jitter for power. Right? So if I want to make a very low power oscillator, I'm going to have to sacrifice something. Okay? The other issue with these synchronous networks is that they often look like this. Okay, so this is one high power like leader, master, and a whole bunch of slave nodes. And they're often not the same. Okay, so one is like a high power radio, the others are relatively low power radios. That's not necessarily so great for IoT. If for IoT, I tend to want more of a mesh networking type paradigm. I want something like this, okay? And probably these are all going to be the same in that case. Because obviously, if I put two of these networks together, what happens to that node? Who does it listen to? That becomes a complicated problem. So this is another thing that I'd like to be able to solve. I'd like my synchronous wireless network to scale better, okay? It doesn't really scale very well, so there's a challenge with that type of network. And I also want it to be made up of more symmetric type of radios. I don't want to rely on all the different types of radios. So by the way, I'm not just pulling this out of a hat. If you look at Zigbee radios or Bluetooth radios, any of these things that support what's called a scatter net, okay, for those of you who are familiar with that term, which is a kind of scaled mesh network, they are all asymmetric. They all rely on kind of big guys and little guys, and only the little guys are low power. Okay? So what do we have in devices that maybe we can use? Maybe spin torque oscillators? I don't know. I mean, maybe that's a possibility for timing. The problem with these, I mean, they're oscillators. They are oscillators, so it kind of fits into that category. The problem with these is that they have terrible characteristics, right? They're tiny, which is good. They're noisy, which is bad. They're highly variable, which sounds bad. Turns out not so bad. And they lack spectral purity. Okay, so they're not necessarily great for RF applications yet. The question is, can we do something to fix this? Okay, and I think based on my previous work that you can. Okay, so I'm showing this something that looks like nonsense to you, which is a picture of fireflies. Okay, one of my friends once said to me, if you have a hammer, everything looks like a nail. So this is my hammer. I'm just warning you up front, okay, which is coupled oscillators. Okay. So this is a picture of Southeast Asian fireflies. And Southeast Asian fireflies do this very interesting thing, which is that they all congregate in a tree and they flash synchronously to attract mates. Okay? And this has been extensively modeled in the literature as this thing, okay, this state function, which is basically a relaxation oscillator, right? So it's a monotonically increasing concave down state function, okay, that is modeling the firefly. And what this network does is, obviously, these fireflies don't have watches and they don't have GPS, so they're relying on local information in order to synchronize. So when an oscillator reaches the end of its cycle and resets, it sends out a pulse, okay? And that pulse then couples to all the neighbors, okay, or any of the neighbors that hear. And if we look at the progression of this, it kind of looks like this, okay? So you can see that this reaches the end of its cycle, it couples, it accelerates this oscillator, that one then, okay, so they accelerate towards each other. It's a nonlinear process, which is why it works. So they basically arrive at a fixed point. And this is kind of the function that is, this is a cartoon of the function, so you can kind of see how it happens in real time. So it's pretty cool. And from a circuit designer point of view, it's extra cool because it's simple. Okay, and this is just sort of, I don't want to spend too long on this, but this is just the mathematics behind it, a really, really glossed over version of the mathematics behind it, which is to say that this, the original paper modeling this was written by Marollo and Strogatz, and it basically says that for a group of n identical oscillators, it shows that this will always happen, okay, for a group of n identical oscillators, as long as this is met, okay? And all this is saying is monotonically increasing concave down. Okay, that's what that says. Those are the requirements for the state function. It's actually relatively simple. The paper's not simple, but that's simple. And so just to show you that we've actually done extensive work on this, we've built this in circuits, and we've shown that even for pretty crappy circuits, it works. Okay, so we're able to basically build a network of 4 oscillators that are wirelessly connected, and we can show that for a period of about 6.7 microseconds, we could get jitter down to about 0.2 nanoseconds. Okay, and so that's actually quite interesting. So why does that happen? Why is the jitter low? So in order to understand this, and I'm not going to do a mathematical treatment of this is going to be quite qualitative, but in order to understand why this happens, we did a study of, I think this was 50 or 100 nodes, I can't remember. It's either 50 or 100 nodes that we did in MATLAB, and we found some interesting characteristics. One thing that we found was that if we made all of these oscillators identical, okay, meaning that their frequencies were exactly the same, but they had noise associated with them, their relative jitter was terrible, okay, and this is the relative jitter, really terrible. But if we made them different from each other, the jitter got better. Okay, which is kind of interesting and has, I think, pretty interesting implications for new oscillators, for spin torque oscillators, right? Because they're probably not going to be identical. Okay, so why does this happen? Let's understand why this happens. This happens because it turns out that each cycle, even though this is a symmetric network and there's no master, each cycle there's a node that starts it. Okay? If that node that starts it always starts it, then everything gets the jitter characteristics of that node. If the node that starts it is always changing, then the relative jitter tends to be terrible. Okay? So we call this leader switching. And it's a very interesting characteristic. And so we could show that as you increase the relative difference up to 1%, you could basically get rid of the relative jitter. Okay, 3 minutes. I'm almost done anyways. Okay, so what is the implications for devices? So there's a couple implications for devices. One is that coupled oscillators and new devices can perhaps be made better by using these kind of algorithmic effects. And I have seen in the literature, even though obviously I'm not a device person, I have seen in the literature that there are actual spin torque oscillators that can be converted into relaxation oscillators. So I imagine something like that could be used to time wireless networks. Okay. Injection locking this doesn't necessarily just have to be for wireless. That's the point I'm trying to make here. That this works for wireless, but it could also be used as a form of analog communication. Okay? And finally, this is also all of this coupling of oscillators. I know it's been applied to associative memories, but it's also interesting for that kind of application. So the oscillators are very interesting as an analog communication block. Okay, so one last thing I'm going to mention, I think this is really maybe my next to last slide, is that I obviously am very interested in these coupled oscillators as a means of communication and clocking networks, but they can also be used to communicate analog information. Okay, and what we're showing here is that if we take basically a set of nodes, and they all have whatever their originating frequency is, but one of them is faster than the others by a little bit, and then we make the maybe one of the ones in the middle, we make that much faster, that basically because of this characteristic of the network, all of the other oscillators will follow that one. Okay, so all of the oscillators take on the frequency of the fastest oscillator. So this is kind of interesting, right? Because this is a means of potentially communicating information, analog information, in a broadcast sense, where the network no node has to be connected to everyone in the network. It's a loosely connected network. So it's kind of an interesting implication of that. Okay, so what happens when the radio is off? I think this is actually my next to last slide. I'll gloss over this a little bit. Option one is that we can power down just the RF blocks and stop clocking back-end baseband processor to maintain state, and that will result in leakage. Right? So we'll just turn off the RF, but everything else will stay on to maintain state and programming. So when we've actually done this with our radios that were duty cycled radios, what we found is the following. The transmit power was mostly dominated by leakage. Okay. And the receiver power had leakage as well. Okay. So it turns out that when you're getting to very, very aggressively duty cycled radios, leakage really matters. So if we have, for instance, state holding logic, okay, something that's non-volatile, it'll actually make a difference for wireless communication systems like this. More of a difference than you think, because when you're running at very, very low duty cycles, leakage does tend to dominate. Okay. And this is kind of the concluding slide. So what opportunities do I see in analog wireless for new devices? One is obviously this for asynchronous communication and wake up. We can use devices with very steep subthreshold slopes, okay, to enable turning on and off. The second is this idea of using maybe spin torque or related relaxation oscillators for network timing and computation, okay. The third, which I haven't really talked about, is it is also possible to couple harmonic oscillators, or even to use coupled by injection locking, but it is that has some disadvantages in terms of that it requires continuous coupling. But we can use this pulse coupling to regulate harmonic oscillators also. So that is another interesting characteristic. And finally, that non-volatile memory can also help with creating low leakage off states. Okay, so I think that was the end of what I wanted to talk about. I hope I haven't run too much over. Okay, thank you.
Thank you very much.
Okay.
I think we could take one question, if there's a question from the audience.